Thank you for coming.
Thank you. Let me set up. Here we go. Hello everyone, my name is Linda. I'm an enthusiast level programmer. I'm a children's book author, a storyteller, and an illustrator. I'm also going to try to work magic with this microphone that seems to be doomed for day one, so apologies if it's going to crackle at some point. We'll do a quick save for that. I'm the co-founder of an organization, a non-profit that teaches young women programming. It's called Rails Girls, and in the 9 years of Rails Girls' existence, it's been organized in 270 cities around the world. I just checked, and it doesn't include Thessaloniki, but it includes Athens, Greece. But today I'm not going to talk to you about diversity. I'm not going to talk to you about getting more women into technology industry. I'm going to talk to you about rekindling our excitement and wonder and the magic of technology that we've all felt at certain times in our career, especially at the early days of our career. But that sometimes gets really hard to remember amid the technical debt, amid project meetings, amidst all of the stuff that bogs us down as developers. My personal journey into the world of technology started when I was 13, but I really fell in love with programming when I discovered Ruby, the programming language. I'm not sure if there's that many Ruby developers in the room today, but Ruby was the first language that allowed me to express myself in the way I felt most natural. And I was studying these computer science books, and every time I would run into something that I quite didn't understand, like what is object-oriented programming or what is garbage collection, I would try to imagine how a 6-year-old girl would explain this concept. And that's how the character of Ruby was born. She's really fierce, really bossy, imaginative, and lived for the first few years in the margins of my computer science books. Something funny happened at this point in my brain. You know how there's people who see math as numbers as colors or math as colors? I started to see the world of technology through stories. And I imagined that, wow, if Apple was a character, it would probably be the snow leopard who's beautiful and likes well-designed things but doesn't want to play with the other kids because they are just too messy. And if Linux was a character, it would be obviously the penguin, who would be really, really efficient, super smart, but somewhat hard to understand at times. And if Google was a character, it would be the green robots who grow up really quickly, and there's a bunch of them, and they change every single day, but they are kind of friendly, and they are kind of powerful. And I went to my mom with this idea, and I told, what if we were to tell the story of technology through stories and characters and this colorfulness and liveliness that I personally see in the world of technology? And my mom tells me, Linda, that's a horrible idea. That sounds like a Soviet propaganda book from the 70s. Why on earth should kids understand how big technology companies work and think? Well, here's the reason. Governments don't reach billions of people anymore. Religions barely reach billions of people anymore. But big technology companies like Facebook, Amazon, Google, Microsoft, they reach billions of people every day. And it pays to pay attention to what kind of value systems and ideas those companies have. So I started with this idea. If code truly is the next universal language, instead of grammar classes, we ought to be teaching poetry lessons. And what I mean with this is the same way we don't learn Finnish or Greek or English only by conjugating irregular verbs. We learn a language by speaking it, by being immersed in the language, by writing, by singing, by dating boys in that language. We learn a language by using it. And even though technical and programming languages are not natural languages, it's a really narrow way we've exposed new generations to the world of programming so far. So more poetry lessons, less grammar classes. And when I show people different programming languages, they usually panic. They go, oh my goodness, it took me 10 years to learn English. How on earth am I going to be able to manage all these different programming languages? But the good news is that even though programming languages differ, especially among the programmers a lot, there's some commonalities across different programming languages for sure. there's things that different programming languages share. And in addition to thinking that, oh, I should make a storybook about the wonderful characters and values of the world of technology, I figured there are these underlying topics and concepts that occur across programming languages. So what if we teach programming before the syntax? What if there was a way to teach the thinking structures of programming prior to introducing any kids to the semicolons and the parentheses of actual programming languages? And I think it's a wonderful thing that we have so diverse tools to teach kids programming nowadays. We have everything from the puzzle-based coded.org exercises that are free to do and translated into a bazillion different languages, all the way to things like Scratch that offer you an open-ended playground. But my interest and my question was, where do stories fit into this equation? If on the other end we have puzzles, and then on the other hand we have playgrounds, where do stories fit? Because after all, stories are the way that we humankind have always learned about the world. We've learned about ourselves, about each other, and we've learned about how the world works. And there were very few stories about the world of software that I knew of. So I came up with stories around little Ruby, and as mentioned, she's 6 years old, and when Ruby's dad tells Ruby, "Oh, Ruby, we're running late from school, you need to dress up really quickly." Ruby, she does dress up, but she leaves her pajamas on because dad didn't specifically first tell her to take the pajamas off. And when Ruby is told that, "Oh, Ruby, your room is a mess, clean up all the toys," Ruby cleans up the toys, but she leaves the pens and papers on the floor because, come on, Dad, pens and papers are not really toys. And there is a chance that I'm definitely raising the most obnoxious generation of kids ever. But they do learn something very profound about how to speak to a computer. Namely, that you need to give very exact commands. The commands need to happen in the right order. You need to be very careful when you name things. And most importantly, that even the biggest problems in the world, they are just tiny problems stuck together. And that's the thing I'm most jealous about for engineers. And I figured that there is this gap in the way we're teaching programming for kids. Because when we get started with programming, we have all of these different types of play and joy in it. And I spoke with the people at Lego who showed me this chart about different motivations for play. And Lego, who probably knows most about play and constructive play in the world, they say that there's 3 types of play in the world. There's the achievement-based motivation for play, there's the social motivation for play, and there's the immersion motivation for play. But for some reason, whenever we talk about programming, we easily go into the achievement mode of play. We talk about points and challenging others and provocation and domination. We talk about gamifying coding. But in reality, everyone here knows that there's so many different aspects of coding and programming. There's the joy of helping one another out in the open source communities. There's the joy of finding and giving support. There's the joy of collaborating together, exploring, finding a new way of solving a problem, and for some of us, escaping real-world problems. And somehow I wanted to tell stories, but also use all of these different aspects of play while teaching this next generation about technology and computers. And none of this is really new for the pedagogists in the room. Because after all, it was Jean Piaget already in the 19th century who said that you don't learn a new discipline by just only being given a pre-organized vocabulary of concepts. You learn things by doing them, and in the same way we ought to be giving kids a playground where they can experience technology hands-on. And it requires us to ask questions that we as engineers and programmers are not definitely equipped to ask. I think a comfortable question for many of us in the classroom situation would be something like, what is a loop? Define a loop for me. But rather, in order to get more people excited about the joy of programming, we might ask questions like, how does a loop feel like? So, an example of how you might go about teaching these things for kids is from Ruby's world, a dance party. And Ruby's favorite dance movement is clap, clap, stomp, stomp, clap, clap, and jump. And we practice with the kids a for loop by repeating 5 times this sequence of dance movements. We practice a while loop by repeating this dance sequence while I'm standing on one leg. And finally, as homework, the kids repeat this dance sequence and practice an until loop until their mom gets really, really frustrated at home. And hopefully, in this way, the kids will have a very kinetic, very physical experience of what a loop feels like. Then they might go into a visual programming language like Scratch or Blockly and make out a loop out of building blocks. And only then might they go into code and practice, this is how you form a loop in JavaScript or Ruby or Python or .NET or whatever. And very importantly, often as educators, we forget to give context, the why for all of this learning. Why am I learning about the concept of a loop? Well, because when you write a video game, there's all sorts of loops inside of it, like keep moving the hero until it hits the enemy. Or if you're making a website, you might write a for loop, like check the password 3 times before locking the account. And I think in this way we can make computer science more approachable, more colorful and more fun for the whole generation of kids. And turns out there's actually a word for these skills. When I was starting my children's book project, I had this vague idea about concepts that go before you learn the syntax of code, but turns out there is a word for this, and it's called computational thinking. And it includes concepts like understanding the concept of an algorithm, or decomposition, or abstraction, or logical and critical thinking. But even more importantly, it includes practices, like the practice of persistency. No programmer writes the perfect code on the first go. Practices like creativity, collaboration. And when we're creating a curriculum for the new generation, we need to balance these both practices and concepts together, not only the concepts. So, turns out there was quite a big appetite for a book like this. 4 years ago, when I was a first-time illustrator, first-time author, with a fledgling idea about what a future of coding curriculum might look like, I put this project on Kickstarter. And I have met enough parents, Ruby programmers, throughout my travels with Rails skills that I felt that if I ask for $10, probably there's going to be enough backers for me to self-publish my first little book. Turns out there was much more people who were excited about this project, because for the first 30 days that this project was online on Kickstarter, it ended up gathering almost $400,000 worth of pre-orders from all around the world, from Amman to Australia, from Belo Horizonte to Berlin, all from adults, parents, teachers, and community members who felt that it's important to have a more diverse group of people learn these skills of 21st century. This $400,000 was also 20% of the annual book exports of the entire country of Finland, where I came from. And I was a first-time author at this point. I was panicking, I was crying and figuring out, like, do they understand that I don't have a book here? This was a video, this was an idea, this was a concept, but it's not done yet, and I have no idea what I'm doing. For the past 4 years, I've worked really hard to get a sense of what I'm actually doing, and Hello Ruby has been translated into, I think, 24 languages right now. Not a Greek version out there yet, so if you have contacts with publishers, come talk to me while we have her over there. And beyond only a book about computational thinking and coding, it's actually growing into a series of books about computers, about networks, about machine learning that explain this more and more technical world for our children and a little bit for us adults too. And the reason why I feel like these topics are so valuable and important is this. A few weeks ago, I was reading this essay. It was from UK, and it said that kids recognize Bulbasaur better than Badger, which meant that kids had more vocabulary to describe Pokemon species than things that existed in the natural world. They didn't recognize birch trees, but they could recognize Pikachu. And the writer was obviously very worried. What happens in a world where we don't have the language to express and explain what happens all around us? And maybe I'll swap that. No worries. So The writer was obviously worried, so much better, thank you. The writer was obviously worried about a world where we don't have words or vocabulary to express the phenomenon around us. Oh, nice. I'm going to do all of the tech difficulties out of one go, so we don't need to worry about that in a moment. But that made me think that actually it's the other way around too. We have this whole group of people who don't know what an algorithm is, who don't know what a server is, who don't know what a DDoS attack is. And the world of technology is full of these words that are black boxes that take in a lot and let out a little. And how do we make and give this vocabulary for kids to understand a world that is more and more built with computers? So the word algorithm, it's a scary big word for normal adults. Or the word DDoS, like how do we explain denial of service attacks for people and kids who just hear it and read it from newspapers? And what about the internet? How do we explain what the internet is for a generation of kids who've never heard the modem sing-song out aloud, who've never turned off the internet, who grow up with internet surrounded and everywhere around them? So one exercise I did with kids to sort of figure out answers for these kinds of questions was an exercise that had to do with data. And there's a lot of different kinds of data we collect about humans online. We collect service data and entrusted data and incidental data and behavioral data. And I started with the kids by doing a data selfie. So I asked the kids to log for a few days every time they searched for something they did online, every time they watched a video online, every time they gave thumbs up for something online, every time they went somewhere with their phone. And they came to the school with their data logs, very proud, showing me all of the data that had been logged about them. And then we cut these pages into pieces, and we used clothespins to attach these pieces of paper on their clothes. And I asked the kids that, hey, we're going to play a round of Tag Your It. And we're going to choose Facebook and Amazon and Google amongst you. And your role is to take all of this data and protect it from all of these kids who are trying to snatch it from you. And the kids have a marvelous time. They run around and they have a really fun time. And finally everyone loses their data because Facebook and Amazon and Google are that good. And we have a huge piece of paper on the floor. And I asked the kids to go and collect a few points of data again. And they might come up with something like a boy who's watched turtles videos and likes puppies on Instagram, and they've been to Helsinki and Thessalonika with their mobile phones. And the next step is I give them the front page news of the said country. And I've blocked out a few photos, a few titles, and a few ads from the page. And I asked the kids to redesign the web page based on how the persona they've just created out of the data scraps might enjoy it. And we get into a really interesting discussion about what it means that everything we see online is tailored to our behaviors and tailored to the data we provide to those search giants. And why it might be a good thing, but why it also might be problematic. And the interesting thing here is the 6-year-olds were all about this exercise. They were very philosophical, very bold. And then I go home and I show this to my mom, and my mom is like, oh, that's how Facebook knows that Zalando, I was watching this exact dress on Zalando and knows how to show the really like the right ad for me at the right time. And I'm like, it's not an accident, it's an algorithm. And we as a community, I think it's our responsibility to open up these black boxes, to make them approachable and make them understandable for the general public. They are not going to do it for themselves. It requires work from us as technologists. And more than coding, more than programming, I think my work nowadays is about preparing kids for a world where every single problem is going to look like a computer. But those problems are not going to be solved with the engineering brain of the current population of engineers. We need a radically more diverse group of people to think about what kind of problems are worth solving and how we ought to be solving them. And that kind of makes me think a lot about the way we talk about technology for kids.
I know in a lot of countries we have this big discussion about teaching kids coding and programming, and I think it's really important. But I think it goes beyond that. I think it goes into understanding what computers are. And there is beauty in computers that I wish every child would have a chance to see. Because in the past 30 years, computer scientists have done marvels. They've built abstraction layers on top of each other to the point where we don't need to worry about how the lowest level of computers work anymore. We don't need to worry about the assembly level code or the binaries or the switches. We can play our Angry Birds or browse our Facebook without having to worry about the nitty-gritty of technology anymore. But at the same time, the computer scientists have stolen something very profound from us, the understanding of how a computer works. I'm somewhat jealous to the people here who grew up in the 70s because you could actually touch a transistor, whereas my generation, you can jam 300 million transistors at the pinpoint of a pen, and there's no way of understanding how these magical, beautiful devices work for us anymore. And sometimes I wish that I could shrink myself to the size of a silicon chip and understand really from the inside out how a computer works. But unfortunately, that's not possible unless you're a children's book author. So that's exactly what I did with my Ruby. And in the second book of the Ruby series, she's really bored at home and she goes into Dad's office and she types in the password for the computer, but the computer doesn't work. And the white mouse next to Ruby, it wakes up and says, "Oh, Ruby, I've lost touch with the cursor. Can you help me find the cursor?" And Ruby says, "Of course, I'm the best computer debugger I know of." And she's never noticed, but there's this tiny hole next to the computer, and they make themselves really, really small, and they fall deep, deep, deep inside of the computer to meet the electricity, the base layer of a computer that is made of billions of tiny switches that only know how to go on and off, on and off. And pretty soon they realize that the bits are really boring. There's no way that they can help Ruby find the cursor. They only know how to go on and off, and you need 8 of them to make even the simplest of things, and they know that they need to climb higher. So they climb higher and they meet the logic gates that takes those bits and turn them into a little bit more complicated things like puzzles that Ruby needs to solve. So here's the AND gate. It's a really interesting mixture of logic and math. And the AND gate asks all sorts of funny questions from Ruby. Like if Ruby says, "Oh, AND gate, I'm Ruby and I just fell in a puddle." If the AND gate is given 2 statements like "I'm wet" and "I'm cold," it says that's true. If the AND gate, and that's another way of saying the same thing, and that's another way because computer scientists like simple things, they like using numbers, that's another way of saying this thing. If you try to be a little bit cheeky and tell the logic gate, the AND gate, something that is not true, it will catch it up immediately and say that, "Oh, I'm warm and I'm wet." That's false. That's not true. And this is another way of saying the same thing, saying 0 and 1 equals 0. And here are all the different ways Ruby can communicate with the logic gate. And here's the way mathematicians would write this thing. And this is a way of making logic gates, things that we study in university, approachable for kids. The OR gate is the next type of a gate Ruby meets. The OR gate is a little bit more relaxed. It's not as exact as the AND gate, and it gives more way for Ruby. So the OR gate takes statements, and even if one of the statements is true, "I'm wet" or "I'm warm," it says that seems to be true. And then there's the final, and here's the mathematical way of saying the same thing. And here's the final gate, the NOT gate. This is the favorite of the kids all the time because they always like inversing things. So whatever you say to the NOT gate, it gives it back in the inverse format. And here's the math way of doing the same thing. And the crazy thing is that computers are made of these gates. Computers are made of tiny bits that are made into logic gates, that are made into more complicated things. But pretty soon Ruby and the mouse realize that, oh wow, the logic gates are not going to be much help. We need to go higher. So they go, skip a little bit. So they go all the way to the hardware layer where they meet the CPU that is really good at giving instructions to all of the other components, but is really forgetful. It can't remember anything, so it needs the help from the RAM and the ROM and the other components inside of the computer. But the hardware can't really help Ruby out either. So up and up they climb until they meet the operating system. And the operating system says, it's been a really chill day for me. I haven't seen the cursor either. There's not much happening here. And I'm not going to spoil how they find the cursor. To do that, you need to read the book. But I think the most important sense the kids get from this journey is this idea that a computer is built on abstractions. It's built from the lowest level, from the bits to the logic gates, the hardware to the operating system. And while computers might seem like magic, they are not magic. They are magical. They are not magic. And having a robust understanding of how computers work, I think will help kids to feel more secure, to feel more self-assured in this world that is full of computers. One exercise that I really like doing with kids is this exercise where I ask them to draw what is inside of a computer. And if I were to do the same thing with you guys, you would probably give me a bunch of empty papers, because that's what we adults do easily. We are scared of things that we can't understand perfectly. And the cool thing about kids is that they come up with hypotheses. And I've had kids who've drawn me inside of a computer. There's all sorts of content. There's games and apps and files, and they are right in some ways. There is apps and software inside of a computer. I've had kids who are future computer architects who describe computers as these interconnected abstract networks of components. They are right too. That's a computer as well. I've had stenographers, kids who have these metaphors of explaining how computers work through theater or through housekeeping or shopping, and these guys are really close to my heart because this is how I explain how computers work. I've had kids who explain to me that inside a computer there are these tiny, tiny gears that go on and off. It's this steampunkish way of thinking about the computer, and while they are not right, computers are not mechanical in this way, I think they have this idea about the digital computer that it's made of tiny, tiny interactions. And then finally, the favorite kids of mine, the kids who draw electricity in some way, the kids who try to explain what transistors are, the kids who try to combine all of these things together, and the kids who again understand that while computers might look like magic, they are only magical. Computers are based on logic, and they are based on things that we humans build and humans do, and we humans have ownership over them. Another step in this exercise is one where I give kids a paper computer to build. And this is online also, so if you want to go home with your kids and build a paper computer, you can do that. It's a really fun activity. We cut out the different components and we discuss what each of them does. And the kids are so proud when they've built their paper computers. They are really bold about what they do, and they come up with all sorts of beautiful exercises and play around this paper computer. Once I had a little boy who comes to me and says, "Linda, I like printing Lego coloring pages on my dad's computer. That's like the best thing I know." And I say, what if your computer had a button specifically designed for printing Lego coloring pages? And he goes and he designs a little button for his computer to print out Lego coloring pages. But pretty soon he realized that coloring pages are boring. What if his paper computer could print out real Legos? What if his paper computer could print out toothbrushes and breakfast for the entire family? And Arthur, who's my godson, his mom comes to me and says, "Arthur, I don't think that's possible. I don't think computers can print out Legos." But you know, Arthur, who's 6 years old now, is going to live up in a world where he is going to 3D print his Legos and his Saturday candy. And I think it's up to us as adults to steer and to guide our kids to have this imaginative relationship with technology. But my most favorite story is the story of a little boy whose favorite thing in the world is to play astronaut with his father. And the boy's role is to be the mission control man. And the boy has these huge headphones on, and he is completely immersed in his paper computer, because you see, he has built his very own, very first intergalactic planetary navigation application. And the boy's father is the lone astronaut far on the other side of the room in the Martian orbit, and the boy's role is to bring dad safely back home on Earth. And I think kids who grow up having this kind of a relationship with technology are far better equipped for a future to feel themselves as creators rather than consumers who passively look for YouTube videos or browse through Instagram. And I think that's the role we as technologists can have in our kids' lives. The next step in an exercise is to show the kids these 4 images. I show the kids, who are usually between 5 and 9 years old, a picture of a car, a picture of a dog, a picture of a grocery store, and a picture of a toilet. And I ask the kids, which one of these do you think is a computer? And the kids who we think are so out of the box thinking, so creative, they all cross their hands like this and they go, Linda, are you completely bonkers? None of those is a computer. The computer is the glowing box which in front of mom or dad spends way too much time. Aww. But we talk. And we realize that actually a car is a computer because it has a navigation system built inside of it. Grocery stores, they have all kinds of computers, ranging from the ice cream machine that keeps the ice cream cold, to the burglar alarm, to the teller's machine because you have the Visa cards and stuff like that, to the dogs, which might not be computers, but a dog's collar, it might have a computer inside of it, and that's a good idea if the dog is prone to running away. And a lot of kids talk about robot dogs, and we get into this discussion about what is the difference between a real dog and a robot dog. And then I tell the kids, and I warn you, don't do this if you have kids under the age of 9, that you know what? In Japan, toilets are computers, and there's even hackers who hack them. And that's like a mic drop moment for the kids. There's nothing else that gets discussed for the rest of the day with them. But pretty soon we try to get our act together, and we move on over, and we realize that actually there's hundreds of computers in every single home, because your microwave is a computer, your remote controller is a computer, your doorbell is a computer. And I've collected these everyday objects for kids: tuna cans, keys, books, stuff that you would have every day in your life. And I've printed out these tiny little stickers with an on-off button on them. And I tell the kids that, you know what? For this afternoon alone, you have this magical ability to turn anything in this room into a computer by placing this sticker on the object. And again, the kids object. They say, Linda, this is too difficult. Linda, I don't know the right answer for this exercise. And I tell them, neither does your parent. They just might have heard about this thing called IoT, or the Internet of Things, but you guys are going to be the last generation of kids that remembers the computer as the glowing box with a screen on it. When you grow up, computers are going to be everywhere around us, from your toothbrushes to your teddy bears, and it's up to you to design that future. So, a little girl, she takes a bicycle lamp and she carefully puts the on-off sticker on the bicycle lamp. And she comes to me and she says, Linda, if this bicycle lamp were a computer, I could go on a biking trip with my father. We could sleep in a tent, and this bicycle lamp, it could also be a movie projector. And that's the moment I'm looking for. Not the moment when the kid understands the difference between hashes and arrays and Ruby, or writes the perfect if-else statement in JavaScript. The moment when they understand 3 very profound things, even as professional developer adults oftentimes have a hard time understanding and remembering. First of them is that the world is not ready yet. There's so many things we haven't discovered or invented. Bicycle lamp, movie projector being one of them, maybe not the most important thing, but that still doesn't exist. There's this sci-fi writer who wrote that everything that happens in technology before you turn 30 is according to the normal order of the world, a totally normal, amazing part of humanity. And everything that happens after you turn 30 is somehow weird and unacceptable and like, yeah, not normal at all. And me at the age of 32, I'm observing myself quite a lot and trying to figure out when I'm going to start to see the world as ready, as something that is not to be built on. Well, the second thing the little girl understood was that technology is a wonderful way to make the world a little bit more ready because it scales. It creates wealth around it. And when you make technology, you take the whole humankind onwards because technology has always been the way humanity has made itself a little bit better. And the third and the most important thing she realized was that she herself can be a part of that change. Odds are she's not going to be the next hardware hacker or Steve Wozniak of the future, but for a moment there, she had the self-efficacy and agency to believe that she could be the inventor of the bicycle lamp movie projector, and I think that's the thing that we ought to be safeguarding in childhood, but also in our own adulthood. So how do you explain what a computer is for a generation of kids who won't have these machines we have today? In order to do that, I think we need to go all the way back to the year 1945 and re-meet John von Neumann, who famously came up with the von Neumann machine. And von Neumann, for those of you who want a little bit of a refreshment into this idea, was the guy who came up with the idea that a computer is any device that takes input data. The data is processed somehow, and out comes the modified data. So this is true when you go on Facebook and you like a post, in goes the data to Facebook server that this post has been liked, out comes the updated like count. And this is also true when you sit in a car and you forget to put your seatbelt on, in goes the data that someone is sitting here without the seatbelt on, out comes the beep, beep, beep noise we all hate so much. And the world, it's full of data, and it's full of sensors that log those data objects. But the cool thing about the von Neumann machine was the memory, because von Neumann was the guy who said that computers have two types of memory. There's the memory that takes in the data and remembers the data that comes in and the modified data that goes out. But there's the type of memory where you write the instructions on what to do with that data. And that's called code. That's called software, and the programmer is the one who writes it, and that's what makes computers so magical. Because pinball machines can only be pinball machines, tractors can only be tractors, but computers can take 1,000 forms and have 1,000 faces. Today computers are digital, but tomorrow they might be theoretical, they might be biological. And getting the sense of a computer as an input-output machine is, I think, in some ways the most important thing we can do for our kids. Because when I follow this discussion around, say, artificial intelligence, I cringe a little bit. We have so much fear around technology, especially the non-technical people among us. And I, for at least, would like to see a generation of kids who have this very pragmatic idea about technology, who understand that while self-driving cars might seem magic, they are only magical because what they actually do is they take input from the car cameras and they have a process that maps that input into a map and the output is this map where the car can see which way to drive and which way not to drive. And that kind of pragmatic optimism around technology is the kind of thing I think our society needs. Not the discussion whether AI is going to become singularity and overthrow humanity next week or in 5 years or in 20 years. And oftentimes we think that in order to explain these things for a 6-year-old, they need to have a PhD in mathematics or so. But I think it's laziness from our part, because kids understand more than we're willing to give them kudos for. And I've started to toy around the idea that what if I would write a book about machine learning for 6-year-old kids? And I think it's a little about our perception as adults about what is difficult and what's not difficult, about our ability to understand that prohibits us from explaining these concepts in a way that makes sense and is exciting for the smallest of us. So a concept I've started to become really fascinated with beyond only programming is the concept of a notional machine. The idea that in order to survive in the future, our kids need to have a very robust mental model of what a computer is good at, and what a human is good at. And that requires us to ask questions that we, again, are not very comfortable with. We might ask questions like, do computers sense things? Well, sure. Can computers have sensors? Well, sure, but can computers sense things? Can computers have feelings? Can computers create artwork? And these are questions that are changing all the time with the advancement of technology. So one way I approach this with kids is we have this exercise called the art machine. And the exercise starts with me giving each kid an algorithm, their very first algorithm. And for the parents of these kids, algorithms is a big scary word. They think of Facebook and they think of the finance industry, but the kids feel very, very proud about the word algorithm. It's big in their mouth, it's fun to say. And after all, they just know that an algorithm is a step-by-step solution to solving a problem. That's all it is. And they know that an algorithm might be to draw a red circle. An algorithm might be to make a green triangle inside of each red circle. An algorithm might be to connect red circles with a blue line. And when I turn this computer on, this art machine, the kids, they go around and around the piece of paper. And in roughly 20 minutes or so, we've generated this beautiful piece of artwork. And I asked the kids to stand up and we all observe the work we've done. And I asked the kids, again 5 to 9-year-olds, so how long do you think it would take a computer to generate an artwork like this? And the kids look at each other and they calculate, there's 10 of us and it took us 20 minutes, so maybe 200 minutes for the computer, because there's only one computer. But what I tell the kids is, you know what? A computer could probably generate 10 million of these in a millisecond, because this is exactly the kind of task a computer is good at. It's good at repeating sequences of instructions over and over without making mistakes, faster than any human ever could do. But how does this artwork make you feel? And a little girl, she comes to me and she raises her hand and she says, it makes me feel very busy. And another girl says, oh, it makes me think of last summer and the summer vacation I took with my family. And I tell them, you know what? These are things computers can't yet do. Computers can't experience emotions of their own around artwork. Computers can't offer an interpretation around artwork based on their own experiences. They might be able to match the pattern to Wikipedia's example of abstract artwork, but they can never offer an interpretation based on their own experience. And that's at least two things that makes us and computers still very different. And probably the kinds of professions where you need these kinds of skills, creativity, empathy, you need to be able to support other people, to motivate them, are things that for a long time still are going to be among us humans. And in some ways, I think this answer is true for a while still, but not much longer. Because I think every single company will be a technology company in the future. In the past, every single company needed to be a bank in some way, because money was the resource that was scarce in the world. But now with Bitcoin, with smaller and smaller companies doing bigger and bigger things, I think every single company needs to start to think like a technology company. But unfortunately, the narrative around what a technology company is often run by the ideas of operational excellency. We talk about being more efficient. We talk about managing processes. And we forget that a computer can be so much more. And if truly in the future every company is a technology company, I think we've only grasped the surface of how a computer can be helpful for us. So let me give you an example. One of the most famous companies in Finland is called Marimekko. It's a clothes company that is very well known for its bold patterns and for its colorful designs. And Marimekko was started by this legendary founder in the 70s called Armi Ratia. And she said famously that Marimekko, it could have equally well been a flower shop. It could have been a fun fair, but she chose to make clothes because she wanted to project her inner world. And I kept thinking, what if Armi Ratia was a programmer in the 70s? What if instead of making clothes, she could have written code and reached millions of people around the world, and maybe today, billions of people? So a few weeks ago, I had the chance to test this out in practice. I was judging a design-a-thon at the Marimekko headquarters, where Marimekko had invited for a weekend a bunch of hackers and developers and designers to think about and reimagine what the future of this company might look like as they are turning into a technology company. The leadership of this company is really smart. And I got so inspired and excited about all of the enthusiasm around me that I felt that I need to try out something too. So I wrote a script that gathered a lot of the Marimekko product names from their websites, 1,400 or so. And they are really these names like Unikko and Jokapoika and Tasaraita, very iconic, very robust Finnish words. And I figured, what if I feed these names into a recurring neural network that would generate new words and names for these products? Because this is something that we truly feel is something that humans are good at. These are skills, the creativity, the coming up with names for products are skills that us humans excel at, and computer can never replace the creative department of this company. And first, the results were really bad. I let the computer run for a few hours, and it learned, went through the patterns in each different name and tried to learn Finnish out of all the horrible languages out there, one of the worst languages to learn. And the first couple hundred examples the computer gave were horrible. They sounded Estonian, they were rubbish, they were just like mumble-jumble words, and I was a little bit disappointed. But I figured that, okay, the computer has only been learning this thing for a few hours. If I go to sleep and wake up in the morning, let's see what happens. And in the morning, around 4 a.m., I go to see my computer, and it feels like it's Christmas morning and Tamagotchi at the same time. That's how AI makes you feel, and neural networks. And I look at it, and the results are gorgeous. The computer came up with new names like Pyyninpakka, Putti, Pukukka, Tanohalti, Tirkka, Ruitintulla, and I bet you haven't heard that much Finnish yet in your lives, but I can promise you that these are really Finnish-sounding words. And I show these examples to the Marimekko creative department, and they are like, these are actually quite good. Should we be worried for our jobs now? And I say, no. The computer came up with thousands of examples, and I was needed to create the good ones out of them. But it does ask the question, where does human creativity and computer creativity meet, and how could we empower people to think about computer as a tool of creation rather than a tool of consumption or a tool of optimization that we so often sort of delegate the computer to? Finally, I think the title for this talk was 100 languages, and in a programming conference we often would think that that means programming languages. But actually the title comes from a small Italian village called Reggio Emilia, who after the Second World realized that they had destroyed a whole generation of kids with the fascism, with the Nazis, and they needed to reinvent a way of teaching children, a whole new way of doing community-driven schooling for kids. And this was in the 50s or 60s. And instead of writing a project report, instead of writing a vision paper, instead of coming up with values, the founders of this school, Loris Malaguzzi and his peers, they wrote a poem. I'm not going to read the whole poem, but it states that the child has 100 languages. The child has the language of sculpting and painting and dancing, but so often we as adults and society say that no, you have 2 languages. You have the language of reading and writing. And we say that imagination and science, reality and imagination and fantasy, earth and sky, they don't belong together. But luckily, the child knows better. And I truly believe that if Loris Malaguzzi still lived today, he would say that programming and coding was one of the 100 languages of the child. I think technology is far too important to be left for technologists alone. And we need more diversity in the people who are building these tools and solutions. But the good news is that the history of computing is full of this interdisciplinary, colorful, wonderful people. The world's first programmer was Ada Lovelace, who was the daughter of a poet and a mathematician. So Ada's mom was a mathematician, and Ada's dad was Lord Byron, the meandering poet who had a lot of affairs and was a very womanizing man. And Ada's mom obviously was very pissed at him for most of their marriage. And she said, my daughter is going to have a rigorous mathematical education, none of the poetry nonsense for her. So Ada, for her, of a woman, did get a really rigorous mathematical education. And she hung out with Charles Babbage and the other smart people in London. And when Charles Babbage was building his analytical engine and everyone was really excited about building a calculator, Ada was the first person to realize that actually what they were building was not a calculator. It was something bigger. Because Ada was the first person to realize that a computer, while it can crunch numbers can represent logic, and with logic you can represent anything in the world. And that's why we call Ada the first programmer in the world. But she's not the only interdisciplinary person in the history of computing. We have another guy called Claude Shannon, who in his undergrad days, he was really into this eclectic logic and math. He took philosophy classes and he fell in love with the work of George Boole, a guy who lived around Ada's age, who came up with these really abstract proofs and things that didn't really make sense at the time. And then Shannon went on to study in MIT, and he studied electrical engineering, and he was the first person to realize that, whoa, these Boolean algebra, these rules that George Boole came up with 200 years before, and electrical circuits, they actually map one-to-one to each other. And that's why we have the modern transistors, that's why we have the modern computers, because Shannon was interested in more than one thing. And now that we're here in Greece, I think it's really fascinating to think that George Hinton, the guy behind all the advancement of deep learning in the recent years, he's actually the grandson of George Boole, and we can map from George Boole almost direct line to Aristotle. And it's a fascinating thing to think about when so often we think about computer science and we think about computer science as the science of studying the computer. Whereas I think that computer science is using the computer to study the problems in the world. And this field only advances if we can invite the world in. If we can get more Booles and more Aristoteles and more Ada Lovelaces to get excited about building the computer of tomorrow. Because technology is built on humanity. These two things are intertwined. There's no way of taking them apart. The very first computers in the world, they were humans who were really good at calculating long series of numbers like square roots or powers of 2 in an era where there were no calculators. And in some ways, I do believe that the very last computers in the world, they will be human too, again. And it's especially cool to say this here in this room in Greece, because in order to understand the future of technology, I think we need to understand the history of technology. If we think about technology today and being technologically literate, we might talk about coding or social media skills or stuff like that. But when we think about technology, yesterday's technology was a combustion engine. Technology before that was a bicycle. And being technologically literate at that era meant probably being able to ride a bicycle or build a bicycle. And we don't know what the future of technology looks like, so we don't know what the literature skills of tomorrow look like. But we have the definition. It comes from Greek. And the Greeks said that technology is problem-solving tools to solve a problem. But they went further and they said that it's not only the tools, it's also the skills and competencies that us humans bring into the problem-solving situation. So technology and humanity are intertwined and always have been. But for some reason, we adults often think about two separate worlds. Technology and humans, logical, mechanical, machine-like, emotional, creative, human-like. Luckily, the kids know better. I asked a bunch of 9-year-old kids in Helsinki in the English school to define to me what is technology, who uses technology, and what is it used for. And this is my favorite answer from a 9-year-old who says that technology is electricity that loves. Can we just pause there for a moment, because this is such a poetic and beautiful way of defining technology. Technology is electricity that loves. And she goes on and states that it is used to play. I use it to have a conversation with my mom. We use a WhatsApp application. And then finally, and probably most importantly, people uses technology. Thank you very much.
Okay, good thing this is the last presentation, because I wouldn't want to be the person who has to do the after this. Thank you very much. Thank you very much for this. It was very inspiring. Thank you for coming. We have some time for some questions. We have all the time in the world for some questions. I'm going to ask the first question because I have all the microphones. So we kind of perceive the world, especially devices, as their own black box. And for me, the other day, I kind of disassembled my car to work on it, and I realized that it's a thing that people built, and it's a lot of components together. It wasn't, I kept thinking of it as one thing, but it turns out it is, somebody made it, and it has components. So when you explain to kids that computers are not magical, it's not just a box that sits there, it has components in it, and you tell them how they work, what happens, like what do you see happening when it clicks and they realize that they can understand how things are inside the computer?
I'll tell from my own experience, because I don't have a degree in computer science, and everything I've learned, I still learn every single day new things. So the moment when I realized that the thing that Claude Shannon realized, that the connection between the Boolean logic and the electricity, I felt like I fell like into the matrix. Like all of a sudden I could see things in a different way, and the whole world like, whoa, what happens? Probably it feels like acid or something like that. But it's this sense, I think the most important thing people get is the sense of ownership and the sense of self-agency in that moment. Not the understanding alone, but the feeling that you are in charge, that technology is not in charge. And I would encourage all of you to talk with your parents, with your neighbors, people who don't work in the technology industry, because here in our own cozy little bubble, everyone understands the new .NET frameworks and the algorithms of the future, but and we are cozy and comfortable, but there's this whole rest of the world that is terrified and has these very weird ideas about where technology is going and what's happening to jobs. And somehow I feel like it's our responsibility to reassure them and to explain to them and have the patience to do that. I promise my mom is not the easiest person to explain things to, but it pays off for sure.
Thank you. All right, let's take some questions from the audience. Raise your hand, please, if you have a question. Are you robots? What did you just watch? Well, ask some questions.
Yeah, I think I'm the last person between the beer and sort of the
Right, okay. Yeah. All right, okay. Let's remove that obstacle then.
I'm going to be over there if anyone wants to come
and say hi. We're going to be outside.
Yep.
You can talk to Linda all you want. Thank you very much again for coming.
Yeah.